Quantum computers require extreme precision. Quantum control electronics are the vital bridge. They translate fragile quantum data, harnessing the true power of quantum.
Welcome to Module 3, Quantum Control Electronics. This video explores the nervous system of a quantum processing unit, explaining how we bridge the gap between classical software and quantum hardware. It's prepared by Dr. Qureshi, who works at the Center for Quantum Technologies in National University of Singapore. He focuses on quantum computing hardware engineering aspects. Control electronics serve as the vital link. They are the essential bridge that allows our classical software to communicate effectively with the sensitive quantum hardware. While the QPU itself is passive, our control systems act as the master puppeteer. They translate digital code into precise analog signals, like microwaves, to manipulate qubits with nanosecond accuracy. In quantum engineering, fidelity is everything. A quantum state is only as pure as the signal that creates it. Any noise introduced by the electronics can instantly destroy the calculation. The system operates across two environments. Control racks sit at room temperature, while the qubits reside at a near absolute 0.15 millikelvins, waiting for precisely tuned signals to arrive. Our core control loop involves 3 steps: generating clean signals, routing them through conditioning systems to remove noise, and finally reading and reacting to the qubit's output. Signal generation is about sculpting microwaves with absolute digital precision. It is the first step in driving the quantum processor. The Arbitrary Waveform Generator, or AWG, is the heart of this process. It uses high-speed digital-to-analog converters to transform complex mathematical equations into the precise physical waves required by qubits. A quantum pulse is defined by 3 key characteristics: amplitude, which controls rotation strength; phase, which dictates the axis of rotation; and frequency, which must match the qubit's specific energy gap. To prevent accidental excitation of qubits, we use pulse-shaping protocols like DRAG. By calculating specific wave envelopes, we ensure operations remain stable without leaking into unwanted states. To reach the correct frequency, we often generate signals at a lower baseband frequency and use IQ mixing for upconversion, which is more efficient and cost-effective than direct generation. Once the signal is ready, the next challenge is routing it into the cryogenic environment without adding heat or noise. We use a axial highway made of specialized materials like stainless steel or niobium titanium. These materials allow microwave signals to pass while blocking the thermal energy that would warm the QPU. To protect against room temperature thermal noise, we employ up to 60 decibels of attenuation. It is effectively like screaming into a void, ensuring only a clean, quiet whisper reaches the qubit. Finally, we use inline components like attenuators to reduce signal strength, filters to clean the signal, and isolators to act as one-way valves, preventing hot noise from traveling back to the quantum processor. Every cable passing through the cryostat acts as a thermal bridge. Left unchecked, this would overwhelm the dilution refrigerator. We use thermal anchoring to physically clamp cables to cold plates at different temperature stages, siphoning off heat before it can reach the QPU. After manipulating the qubits, we must read their state. The goal of state readout is to extract quantum data without destroying the delicate information held within the qubit. We use dispersive readout. Each qubit is coupled to a microwave resonator. The resonant frequency of this component shifts based on the qubit's state. By bouncing a pulse off this resonator and analyzing the phase of the reflection, our electronics can deduce the state. This signal is incredibly faint. An amplification chain is required. A parametric amplifier at the base stage for low noise gain, followed by a HEMT transistor at the 4 Kelvin stage for power, and finally, a room temperature amplifier for digital processing. Once the signal reaches room temperature, it is still analog. We use high-speed analog-to-digital converters, or ADCs, to digitize the waveform, allowing our logic processors to perform state discrimination and determine if the qubit is in a 0 or 1 state. For advanced quantum algorithms, we need real-time control. This is where fast feedback loops become essential to maintain stability and performance. At the core of these control systems are FPGAs, or field programmable gate arrays. Unlike standard CPUs, they are programmed at the hardware level, allowing them to act as deterministic conductors for the entire system. FPGAs are mandatory because they offer deterministic timing, massive parallelism to control hundreds of qubits simultaneously, and the ability to run custom digital signal processing algorithms on the fly. This speed is vital for quantum error correction. We often have a window of only a few hundred nanoseconds to read a syndrome, calculate a correction, and apply a pulse before the quantum state decoheres. As we move toward thousands of qubits, we face a major scaling bottleneck. Simply adding more cables is not a viable long-term solution. Every qubit currently requires multiple coaxial cables. A system with 1,000 qubits would require thousands of these connections, which would physically crowd the cryostat and introduce too much heat for our cooling systems to handle. Maintaining a 1-to-1 ratio of room temperature electronics to qubits is impossible for fault-tolerant quantum computing. We need a more efficient approach. Frequency division multiplexing helps by combining multiple signals into a single cable. At the chip level, demultiplexing routes these signals to different qubits based on their specific frequencies, reducing the total wiring count. The ultimate solution is Cryo-CMOS. By designing specialized silicon chips that operate at 4 Kelvin, we can move the control electronics inside the fridge, replacing thousands of cables with a single digital optical fiber. This concludes our overview of quantum control electronics. Thank you for watching. If you are interested in exploring further, Dr. M. Fahed Qureshi is open to consulting, joint research, and professional training. Please feel free to reach out via the contact information provided on the screen.